Okay, we're back. So we've got what we're talking about right now is this finitely repeated prisoner's dilemma. And so I added in this one sentence right here. It says, in any finitely repeated prisoner's dilemma, the only Nash equilibrium outcome is all DD. So this is kind of a pessimistic or like a negative result, right? The whole setup here was, oh wow, we always play DD in Prisoner's Dilemma, we get 0-0. Wouldn't it be nice if we could play CC and get 1-1? And so far, what we have tried does not work, right? So what we have found is, well, if you play a finite number of times, so if you announce in advance, we're going to play 1,000 rounds of the Prisoner's Dilemma, then still the only Nash equilibrium is all D, meaning both players just play D in every single period. So you can sort of see where we're headed. There's maybe a little bit of foreshadowing right here where we say in any finitely repeated prisoner's dilemma. So notice that the whole reason that this fell apart is because we had a last period, right? So we could say that in the fifth round of our prisoner's dilemma that will be repeated 5 times, they have to play DD. Well, if you have an infinite number of rounds, you don't have to worry about a last round. There's always an infinite number of rounds left to play at any given moment. So if we're going to talk about playing the prisoner's dilemma an infinite number of times, well, the first thing that we need to do is to figure out how to convert our game scores into like an overall payoff. So let me try to illustrate the problem here. Okay, so the idea here is that we can't just keep doing what we have been doing, of just adding everything up. So this is going to be the infinitely repeated prisoner's dilemma. So before what we did, so with finite PD, we just said, for example, that pi j is equal to pi j1 plus pi j2 plus up until 5. If we were going to play 5 rounds of Prisoner's Dilemma, that's what we did. Well, the problem with doing this with an infinite Prisoner's Dilemma you may hit infinite. And so that's not really what we want. So for example, let me just try to give you a flavor of why the math is going to break down if we try to do the same thing. So if we try to do the same thing, compare the payoff from half of the rounds are CC and half are DD. So that's the sort of first outcome. So this describes what happens in our infinite game. So compare the payoff from that to payoff from every round. Is CC. Right, so, intuitively, the latter should be better, right? Because if every round is CC, you're getting a payoff of 1 every single period. In the first thing that we talked about, where half of the rounds are CC and half are DD, you're getting 1 in half of the periods and 0 in half of the periods. So that should be less, right? But if we do just say, the same sort of idea, that pi of j is equal to pi of j in each period, and extend that infinitely, well, then we have a problem, right? Because, here, I'm just going to sneak in a label here. So we'll call half of the round CC, half are DD. We'll call that 1. And every round is CC. We'll call that 2. Well, so if we do this thing that's going to turn out to not be a good idea, if we say that we'll just add up the scores, then pi sub j from 1 is infinity, right? Because we're going to add up 0 plus 1 plus 0 plus 1 plus 0 plus 1, and we're going to keep going forever, and that's infinity, right? Because, any number you pick, say you pick 1 billion, well, we're going to end up with a score that's higher than 1 billion, because it'll just take, 2 billion rounds. And so what that means is that the payoff from 1 would be infinity. And from 2 would also be infinity. And so this is really unattractive. We really just don't want payoffs to be infinite. And one reason is because we have sort of different payoffs. One really should be better than the other, but they both end up being the same and both being infinity. So the conclusion here is we will not say just that pi of j is equal to pi j1 plus. So that is not what we're going to do. We're going to do something a little bit more clever. And so what we're going to do is we're going to introduce discounting. So discounting, what broadly speaking, what discounting means is that we treat earlier rounds as more important than later rounds. Right? So the idea here is that we're going to say, look, what happens early on it's just more important than what happens later on. Now, there's a couple of sort of reasons for that. The first justification is just pragmatic. It's going to get us out of this problem of infinite payoffs. There's also some economic logic to it, right? If you asked a person or a firm, hey, you're going to either get $1,000 today or you're going to get $1,000 in 5 years, everybody wants the $5,000 right now. And so when we talk about making the early rounds of our infinitely repeated prisoner's dilemma worth more, you can think of that same idea, right? You would rather get the high payoff early on rather than the high payoff later on. Okay, so I'll pause the video for a moment right here, and we'll be right back with some discussion of how discounting works.